Okay. Hello, everyone. I am Andrej. I am the Director of AI at Tesla. And I'm very excited to be here to tell you a little bit about PyTorch and how we use PyTorch to train neural networks for the AutoPilot. Now, I'm curious to do a bit of a show of hands. How many of you actually own a Tesla? OK, a few. And how many of you have used or experienced the AutoPilot, the product? OK, a few. Yeah, so let's see. So for those of you who may not be familiar with AutoPilot, the basic functionality of the AutoPilot is that it keeps the car in the lane, and it keeps the car also away from the vehicle ahead of you. And then some of the more advanced functionality that we've been building for the AutoPilot includes Navigate in Autopilot, which allows you to set down a pin somewhere on the map. And then as long as you stick to highway, the car will do all of the lane changes automatically, and it will take all the right forks to get you there. So that's with Navigate in Autopilot. With Smart Summon, which we only released about 2 weeks ago, you can summon the car to you in the parking lot. So you hold down Come to Me, and the car comes out of its parking spot, and it will come find you in the parking lot. You get in like royalty, and it's an amazing, magical feature. More broadly, the team is very interested in pursuing and developing full self-driving capability, so that's what everyone is focused on in the team. Now, famously, perhaps we don't use LiDAR, and we don't use high-definition maps. So everything that we built for the AutoPilot is basically based on computer vision, machine learning, on the raw video streams that come from the 8 cameras that surround the vehicle. So this is an example of what we might see in one single instant. And we process this, as you might imagine, with a lot of convolutional neural networks. Now, Tesla is a fairly vertically integrated company. And that's also true when it comes to the intelligence of the AutoPilot. So in particular, of course, we build our own cars, and we arrange the sensors around the vehicle. But then also, we collect all of our data. We label all of the data. We train it on on-premise GPU clusters. And then, of course, we take it through the entire stack. We run these networks on our own custom hardware that we develop in-house. And then, of course, we are in charge of the full lifecycle of these features. So we deploy them to our fleet of almost 750,000 cars right now. And we look at telemetry and try to improve the feature over time. So we kind of close the loop on this. So I would like to slightly dive into some of the distributed training that we employ in the team. So the bread and butter for us is, of course, analyzing images. So here's an image. In order to drive in this environment, you actually have to understand a lot about this environment. So perhaps we have to understand the traffic lights, the lane line markings, cars, and so on. So you end up in this very massively multitask setting very quickly, where you just have to know a lot about the scene. So a lot of our networks take on this outline here, where you have kind of a shared backbone that has a number of tasks hanging off of it. And just to give you an idea of the workflows and the kinds of networks, these are typically a ResNet 50-like backbones running on roughly 1,000 by 1,000 images. And then they have these heads of these structures that make sense. And of course, we're doing this partly because we can't afford to have neural networks for every single task, because there's many, many tasks, almost 100 tasks. And so we have to amortize some of that computation. So we put them on shared backbones. So here's some examples of what these networks that we call hydronets, because of the shared backbone and multiple heads, what these hydronets might look like. Is this video playing? It's not. OK, I'm just going to go to the next video that was going to show you some lane line markings and so on. This is a video showing you some road edges that we are interested in for the purposes of Smart Summon, because we have to understand where we can be in this environment. So we want to avoid the curbs in this case. Now, here we are making predictions in the image. And then we are, of course, casting them out and stitching them up across space and time to understand sort of the layout of the scene around us. So here's an example of this occupancy grid. We're showing just the road edges and how they get projected. And the car winds its path around this parking lot while the person is summoning it, and is just trying to find its way towards the goal through this parking lot. So here's how things get stitched up. Now, so far, I've only talked about neural networks that run on independent images. But of course, very quickly, you run across tasks that actually have to be a function of multiple images at the same time. So for example, if you're trying to estimate depth of any of these images, it might actually be very helpful to have access to the other views of that same scene in order to predict the depth of every individual pixel. Or if you're trying to predict the road layout, or if you're trying to steer the wheel or something like that, you might actually need to borrow features from multiple other hydronets. So what this looks like is we have all of these different hydronets for different cameras, but then you might want to pull in some of the features from these hydronets and go to a second round of processing, optionally recurrent, and actually produce something like a road layout prediction. So this is an example of what a road layout prediction might look like for the AutoPilot. Here we are plugging in 3 cameras simultaneously into a neural network, and the network's predictions are not anymore in the image space, they are in the top-down space. So we're looking at the predictions of this network. In particular, here we are showing some of the predictions related to the corridors that are available in this parking lot, where the intersections are and what the orientations of all of these things are. And so the stitching up now doesn't happen sort of in the C++ code base. The stitching up across space and time happens inside the recurrent neural network. So more generally, what our networks start to look like for all of these different tasks and what we're converging on is it looks something like this. We have 8 hydronets for the 8 tasks. They all produce all kinds of intermediate predictions. But in addition to that, the features from these hydronets go into a second round of processing. There's potentially recurrent. And then we have more outputs that are sort of in a top-down view. And then what's special about this is that this is, of course, like a pretty large single network. And every single task subsamples parts of this network and trains just that small piece. So for example, we can be training object detector on one of the cameras, or we can be training a depth network, or we can be training a layout network. All of these tasks subsample the graph and train only that portion. And then if you've trained recurrent neural networks on videos, you'll quickly kind of notice that these are not trivial training workflows. So as an example, if I want to unroll this graph in time and backpropagate through time, maybe we have 8 cameras, we unroll for 16 time steps, we use a batch size of, say, 32, then we are going to be holding in memory 4,096 images and all of their activations in a single forward pass. So very quickly, your typical distributed data parallel will break because you can't hold this amount of memory, this amount of activations in memory of a single GPU or even a single node. So a lot of our training potentially has to combine some elements of distributed data parallel, but also model parallelism and so on. It also gets kind of tricky in terms of training these networks because the typical simplest case might be a round-robin training of different tasks. So you're training task 1, then all the workers in the pool are training task 1, then task 2, 3, etc. That gets out of hand when you have 100 tasks. So instead, what might make sense is to actually have a pool of tasks. And some of the tasks are doing objects. Some of the tasks are doing road layout. Some of the workers might be doing depth, and so on. And these are all very heterogeneous workflows, but they coexist, and they're training different pieces of the network at the same time. And then you can arrange them in synchronous, asynchronous way, or play with this to really squeeze out all the juice out of it. But all in all, if you're trying to train all of the neural networks for the AutoPilot, it's actually a fairly expensive task. In particular, today, we would train 48 different networks that make 1,000 different predictions. This is just if you count the number of output tensors. And it takes 70,000 GPU hours to compile the AutoPilot, at least the neural network stack. So if you had a single node with 8 GPUs, you would be training for a year. So it's a lot of networks and a lot of predictions. And a lot of them must work, and none of them can regress ever. And then you're not just training this once, you have to iterate on this. So of course, there are researchers and engineers in a team that actually have to improve on this. And so as you can imagine, we do a lot of neural network training at scale to get this to actually work. And then we are automating a lot of the workflows. It's not just about the neural network training itself, but everything surrounding that. So in particular, we have to calibrate all the different thresholds. We have a process for that. We have a lot of in-the-loop firmware in-the-loop validation, other type of validation and evaluation to make sure that none of these 1,000 different predictions that we make can regress, and so on. And so the North Star for the team, though, is all of this can actually be automated quite well. So starting with the data set, you can train all the neural nets, you can do all the calibration, the evaluation, and you can really start to see the continuous integration of this. And so the North Star for the team is something we internally, somewhat jokingly, refer to as Operation Vacation. And the idea is that as long as the data labeling team is around and they're curating and improving our data sets, then everything else can in principle be automated. And so we could actually go on a vacation and the AutoPilot improves by default. So that's something that we really try to go towards in the team. I would like to also talk a little bit about the inference aspect of this. Because I talked quite a bit about training. As I mentioned, we have sort of our own backend that our hardware team has developed. We call this the FSD computer. It offers about 144 int8 teraops of capability. Compared to the GPUs that we were using before we introduced this chip, this is roughly an order of magnitude improvement with lower cost. So we use this in all the latest cars that are now coming out of the production line, and we target all of the neural networks to these chips. And the last thing I wanted to also briefly allude to, as you'll notice here on the bottom, we have a GPU cluster. The hardware team is also working on a project we call Dojo. And Dojo is a neural network training computer in a chip. And so we hope to do the exact same thing for training as we did for inference, improve basically the efficiency by roughly an order of magnitude at a lower cost. But I'm not ready to talk about more details on that project just yet. So in summary, I talked about the full lifecycle of developing these neural networks for the autopilot and how we own everything in-house. The neural network is actually fairly complicated and large, and we deal with a lot of problems if we actually want to train the beast. But it's giving us some very interesting results. And the nice thing about this is not only do we get to train really awesome large networks, but we also get to ship them. And so, for example, Navigate and Autopilot has now accumulated 1 billion miles. We've confirmed 200,000 lane changes, and this is a global product across 50 countries or more now. And so that's a lot of forward passes out there of neural networks. And with Smart Summon, this is actually a bit of an outdated number. We now had 800,000 sessions of people trying to call their car to them. And so it's incredible to work on such an interesting product. Finally, I would like to thank the PyTorch team for being incredibly responsive and helpful in sort of allowing us to develop all these networks and really train them at scale and then deploy them to the real world. It's been really an interesting collaboration. Thank you.